Hey everybody, wanted to spend a little bit of time talking about half-life and doing some calculations with it. So half-life is the time that it takes for the reactants to be used half up. So you're going to have half as much that you began with in the reaction. Now that can be measured by mass, it could be measured by moles, or in this case, we can use concentration to measure it, and that's what we will use. The idea of half-life is it's really convenient for us to measure how fast reactions take using half-life because it's easy to determine experimentally for at least first-order reactions, and it's convenient for reactions that go a really long time. We can kind of easily figure out what the rate of the reaction is, and we can figure out the rate law for it, and then we can do a half-life kind of straightforwardly. But for you, I think we're only going to worry about first-order half-life reactions. In order to understand what the first-order half-life is, we should look at the first-order integrated rate law. The first order rate law, remember, is the ln of the concentration of A at some time t equals this. Let me write that a little better. So what we can do is we can take this, and we know that for specifically half-life, based on what we wrote back here, that the concentration at the time, at the half-life, is half of the initial concentration. So we can substitute into the equation half, that the ln is half at that particular time is ln of A naught, and that equals. We can continue to break this down, so we subtract both sides, so that makes that subtract by both sides, and when we subtract natural logs, that means we divide them, so that's the ln of 1/2 A naught over A naught equals negative K T. This cancels, and we get the ln of a half is equal to negative KT. And in the end, and I'm going to erase all of this, when we rearrange and do the math, we get that the half-life is equal to, and this is the symbol for half-life, is equal to 0.693 over the rate constant. And that can be used to either find the half-life or the rate constant in sample problems. So let's do a couple of these. Okay, and so here we have a gas phase decomposition. That's the reaction right here. Okay, and we know that it's first order. So that means that the rate law is R equals K times the concentration of SO2Cl2 to the first power. Okay, and it gives a temperature. At that temperature, the half-life is that many seconds. What is the rate constant? Well, in order to do this, I'm going to go here. So we have a half-life of 2.3 times 10 to the 5th seconds. We're trying to find the rate constant. Well, that's a kind of a simple plug and chug, because we know that the half-life is equal to 0.693 divided by the rate constant. And so now we do the math. We plug in 2.3 times 10 to the 5th equals 0.693 divided by K. And in order to get that correct, you're going to get K equals 0.693 divided by 2.3 times 10 to the minus 5th. This should not be negative 5. And when we do that, we get a rate constant equal to 2.772 times 10 to the minus 6. And then it says at 320 degrees, we know that we get a different rate constant when we change the temperature. But the rate constant is now 2.2 times 10 to the minus 5. It says, what's the half-life at this temperature? Okay, well, we're going to do the same sort of thing. And now we have the rate constant. And so we do that math, and we get 31,500 seconds. So that's the time it takes for that reaction to get to half of its concentration. Now the next problem here, we have a first order reaction. It's the decomposition of N2O5, and it gives the rate constant. And then it gives us some conditions. So what I'm going to do is I'm going to take this and I'm going to transfer this information to my Smart Notebook so I can easily show you the problem. Okay, so I transferred all this information. It's right here. I have the rate constant, and the rate constant is in units of seconds to the minus 1. And then I have the concentration of that compound. And notice that in the problem it gives moles here per liter here. Okay, well, moles per liter, we know that we're dealing with concentration because it's half-life and its rate. So now it asks, the problem asks for how many moles will remain after 2.5 minutes. Okay, so for part A, that says moles. So let's do this. Now, in order to figure out how many moles after 2.5 minutes, this is a time thing. It's always safe to go back to the formula that you were shown. And so what we're solving for here is this variable. So let's plug in the values and then chug along. The first thing that we're going to do probably is we're going to have to calculate what the concentration is. So 0.250 divided by 2. And the concentration here equals 0.125 molar, and that's our initial concentration. So that is going to equal negative K, which is 6.8, what is it, 6.82 times 10 to the minus 3 times T. The T is in minutes, but our rate constant is in seconds. That's a thing, so just keep in mind that 2.5 minutes equals 150 seconds. You have to make sure your units agree. 150 plus, and then the initial concentration is the ln of 0.125, and we plug that into the calculator. When we do that math, we get that equals the natural log of the concentration. So now we do e to the, that cancels that out. And so now we get the concentration of AT is equal to, and then I look at that and I say, does that make sense? Well, the initial concentration is 1.125, and so it definitely went down. For part B of the same question, it says how many minutes will it take for the quantity of N to drop to 0.010 moles. Now, I get that for part A, the question was to figure out how many moles, so we can definitely go to moles here. But we want to know the time for part B. We want to know the time. Well, again, if it's not a half-life problem, you still have to use the first order rate equation. And when we use that, we again plug and chug. Instead of solving for the concentration at time t, we're going to solve for that guy. So it's just another plug and chug. But now, again, be careful of your units. This is in moles. Moles per liter is molarity. The molarity is going to be this divided by 2 liters, and so the molarity is 0.005 0.005 molar. And so we're going to do the ln of 0.005 plug it in, and we do the math. This is negative 5.298, and that equals combine like terms and then divide by the rate constant. And so when we do this, we get t equals 471 it's 472 seconds. And so if we wanted to convert that into minutes, there's 6, we would divide by 60. It's 7 minutes and 52 seconds. Okay, so now let's look at part C to this. Part C says, what is the half-life? Well, the half-life, we can really just do the formula T equals, the half-life, T at 1/2 equals 0.693 over K. And this, of all the problems, is kind of the easiest because all you have to do is plug and chug. The half-life, after you plug it all in, so that's how you work half-life. Half-life is a fairly straightforward calculation, but it's knowing when to calculate half-life and using the half-life that can sometimes trip you up. So there it is. Have a great day.